Okay, let's go with this. See what happens after. At least we have a backup solution. Okay, so welcome. This is a Math for Cryptography class. So I'm very excited because that's exactly what I do. I work in the math department and I develop the mathematics that is proprietary for cryptography. And cryptography itself is kind of like a very interdisciplinary field, very broad, and you can approach it from various angles with components of mathematics, computer science, engineering, all sorts of stuff. So, I mean, I'm trained in mathematics because I have a mathematics degree, and so that's what I like to do. And of course, whatever you do, you need to know what happens on the other end as well. And so I interact with a lot of people in a lot of departments and stuff like that. So I think it's very exciting. There's a lot of different math in crypto as well, because it's not just, we're going to be looking mostly at algebra, number theory, and the traditional bulk of the mathematics, but you do need to know notions about probability and a bunch of other little things that come into play. So I find it a very complete topic, very interesting. So we'll be going along the way, and I'll fill in. There's way more than you can cover in one class. So anyway, on one hand, this wants to be a little bit more advanced class than like a traditional introduction to crypto, where like you have very little mathematical content, but we're not going to go too deep, and hopefully this can be a prompt. And then when you have like more mathematical tools and you can look at more advanced math classes, then you can learn even more about that. Because that was a long process for me, so I expect it's the same for everyone, right? So okay, so before I just wanted to start with a little recap of actually what kind of cryptography, what is cryptography, and what we're going to be looking at. I don't know how much you've seen of cryptography itself. I expect various types of interactions. Have you all heard about cryptography in one way or another, I guess? No? See? Okay, so that's fine. That's fine because, in fact, today's lecture just wants to be a little recap and a little intro to crypto. Okay, and then we'll move away fast, kind of thing. So let's see this. So by cryptography, traditionally is a very old idea of making a message secret, right, and communicate securely. Yes. So in fact, they say, and no one can really actually testify to this, that Julius Caesar himself was using some sort of encrypted scheme for communicating on the field. And the scheme would work like this. Essentially, if he had to send a message, say like hello, he would shift every letter up by a certain number of positions, and would obtain some sort of gibberish looking thing. So for example, if you use this number of positions by 3, then the H becomes K, and the E becomes FGH, and the L becomes M and O, and this is another L, so it also becomes O, and the O becomes PQR, right? So all I've done is move everything up by 3. So it's often convenient to visualize these things. If you imagine that you have the alphabet, right, the English alphabet, you can put it on a wheel, and here I have a pretty tool, right? If you can see, and you can move things by, say, like 3 up, so like this. So the A becomes a C, right? And then we said that the H becomes a K. Did I move? Did I move?
That 2 spaces.
There you go. Okay, so now that should work, more or less, I think. Right, the H becomes a K, and the O becomes an R. I think we got there. Okay, so basically, this is what is called a cipher wheel. And this method of securing information, in fact, is what normally we call a cipher. Okay, so a cipher is just a scheme for hiding your messages. So I can probably remove this here. So this message that we are sending normally we refer to as plain text. Is the plain text that we are transmitting. Right, so imagine this is whatever Julius Caesar was sending on his battlefield. And the hidden version we call ciphertext. Or encrypted text. Okay, so it's a very simple method, of course. I am sure some of you already were doing this in school, like, oh yes, let's communicate securely, like I'll just up everything by 4 or 5 or whatever, and then no one's gonna be able to read my. I used to do that, but anyway, it's a common puzzle in the crosswords. Okay, it's just a very simple idea, but because it's simple, of course, has its limitations, right? So the idea is that I mean this is a prototype of cryptography. Normally, because we are like shifting letters up. Then the way to decrypt this message when I receive the ciphertext is to just shift back by the same amount of letters, and then I recover what the plain text is. Yes, so I can imagine like I'm gonna shift my thing back, and then I obtain my plain text back. Right, so this is normally what we call the shift cipher. Because it works by shifting letters. And in fact, sometimes this is known as the Caesar cipher, when the shift is equal to 3. I believe 3 is the original one, or at least what they claim was the original one. Okay, so of course, as I said, this is a very simple method, and what kind of security can it offer? If I find an encrypted message, all I have to do is try 26 different letters, and I will find something that makes sense, and then the thing is broken. Yes, but maybe in the meantime, the troops already have moved or whatever, and for that kind of scenario, it was sufficient. So this is already one important notion about cryptography, is that you have to understand what tool you're looking for your purpose. Okay, so in general, we think about cryptology as being comprised of 2 very different areas. One is cryptography itself, and the other one is called cryptanalysis. All these words come from Greek, of course, and they are kind of, in a sense, they suggest what they're doing. So cryptology is just the area of studying methods for secure communications, and the cryptography part is about creating methods, where the cryptanalysis part is about attacking and finding ways to break. Right? So this is traditionally what we refer to. I personally work more in this part, but of course, as for everything, you have to know what the other hand does as well. So I often think it's like 2 hands that work together towards a common goal. Right? So the cryptanalyst is not your enemy, is like more like your colleague, and they kind of discuss together, and there's like, okay, I propose this, and let's find some weakness in it, and then we kind of talk back and forth. So let's go back to the idea of a cipher. This, obviously, even yourselves can think, okay, how can I do it better, right? This is a very simple method. All it takes is 26 attempts to break, but can I do it better? Why do I have to shift everything by the same letter, for example, right? I could do this more secure if I used different methods for each letter, for example. And so if I do this, then I have to choose what I shift by the first letter, what I shift by the second letter, and so on. And this becomes intuitively more secure method. So if I do this, then I have to say, choose A, right, B, C, D, E, and whatnot. And then I assign a letter to it. For example, I will map A to C, I will map B to I will map C to S, and this one to Q, okay? And now my key is going to be a lot more complicated than what it was before, right? So this method, I'm not going to fill in, but you do have on your book. So one way to look at this would be as a table, you see, in which you just match each letter to another letter. Yes? Okay. So mathematically, we can think of this, and this maybe is the first hint of math, as a function. Let's call it f for now. We'll be more precise later. That takes the set, let's call it A for alphabet, and maps it to itself, right? And then to A I assign C, to B I assign I, and so on. Right? So it's a function, you see. It's a properly defined function, element by element. And we call it a substitution cipher. Cool. So, of course, it is important that this function verifies some of the most basic, most common, and most important properties of a function, which are, you will tell me, traditionally, for example, I want this function to be...
well, every input needs to have only one output.
Yes, so it needs to be injective.
Right.
Because otherwise there's ambiguity. It is not required in cryptography that this one is also surjective, but in this case it is. In this case it's a bijection. You see, it's a mapping from A to itself. I'm just going to map one letter to another letter, one letter to another, and then I'm done. So in this particular simple case, substitution cipher is a bijective function. So in this case we have a bijection. Of course, if I didn't have the one-to-one property, then decrypting accurately would be impossible, right? So, so then this is a fundamental problem. So here, this is an example of a substitution cipher. Every possible assignment of letters gives me a different substitution cipher. Okay. So we haven't yet talked about the structure. We will do that formally later about a structure of a cipher and of an encryption scheme. But already you can imagine that this thing is called, I mean, what do you have, right? If you have a door and you close it, and then you have a door and you open it, you use a key. And so this thing is called a key, right? This thing is called a key. In this case, the key is exactly the mapping from the alphabet to itself. In the case of a shift cipher, the key was just the number of how many letters I shift by. Yes. So the idea of key is, of course, central in cryptography. It's the most important thing. What we are looking at now, ciphers, and we will formalize that later, are an expression of what we call symmetric cryptography. Okay, and the reason why it's called symmetric is because we have already seen two examples, right, in which the key you can use to open and close the door, in a sense, right? So this corresponds really with a very meaningful analogy to the idea of hiding your secret somewhere secure, like a crypt. I mean, it's the same word, right? The crypt used to be, I'm from Europe, where you put like the bones of your saint or your relics or stuff like under the church, right? And so like it's a door and you just close it. And if you open it, you use the same key in the reverse way. I mean, it's exactly the same thing. So we use here the same key. Here, if I have a substitution cipher, my mapping brings A to C, B to I, C to S, and whatnot, and then I use my key, right? The other user has the same key and use it in the reverse way. So this is symmetric cryptography. Later we will see that, in fact, the focus of this class and a big chunk of cryptography today works with a substantially different paradigm, which is not symmetric at all. Do you have any questions up to now? Okay, so this is looking very simple, right? And there's very little math to this yet, but already you can make some considerations. First, we had the shift cipher. All it takes me is 26 attempts. I really can't consider this to be secure, right? Now, what about this one? What about the security of this crypto system? I have how many keys? Well, every assignment gives me one, right? So the first one, I have 26 possibilities. Like, how many possibilities do I have for A? 26. Once I assign one of them, because it has to be a bijection, I then have 25 possibilities for the B, and then 24 possibilities for the C, all the way down to the Z, which will be just whatever is left. Okay. So you see there's already a component of probability here. We will do more probability than this, but already here there's some basic idea of counting, right, which you have to be familiar with. Of course, this is the number of combinations that you can have. In this particular case, this is 26 factorial possible different keys. Right? So if you know nothing about the key, well, then you have to try 26 factorial times. And of course, this is way harder than just trying 26 times. Okay, so you can see that 26 factorial is that number, 40329, blah, 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 blah. So it's huge, of course. Now, there is usually what is considered to be secure in cryptography. We have certain thresholds. We will talk about this maybe later, but it's the same idea that I was hinting at before. You have to understand what kind of goal you have for security in your specific scenario. When we look at numbers, we use logarithms traditionally, in the sense that we look at what is the number, because the numbers are so big, yes? So 26 factorial is huge. So I just want to know, in base 2, for example, this is 2 to the power of, right? And so if you compute the logarithm in base 2, I think I don't have it here, but in base 10 is
88.
Huh?
Log 2 should be 88.
88, okay, great, thank you. What I was going to suggest is we also have log 10, which is about 10 to the 26, right? Normally in cryptography we use the binary one, okay? But of course, once you have one logarithm, you can always obtain the other logarithms with the simple logarithm change formula. So 2 to the 88 is a decent number. Normally, this day, everything that is above 2 to the 80 is considered unfeasible, of course, because it's way bigger than the age of the universe, and therefore we assume it's not feasible to break, yes? But what we are trying to standardize now is, for example, 2 to the 128. These numbers are, again, decided a priori. If you have something in the order of, say, 2 to the 30, maybe it's too hard for you to break on your personal computer, right? But then, you know, a cluster of computers can do it. It can take 1 hour, 1 minute, 3 days. Again, depends on what your kind of end goal is. Yes. So this that I mentioned here is what we say the idea of computational security. We will see later that we have different types. Computational security is by far the most important notion. Okay, so then substitution cipher is great. We're done, finished. End of the cryptography course. But this is not the case, right? So because even in the case of the English alphabet that we're working with right now, from the next lecture on we'll start talking about numbers. But for now, we can still imagine that we're working with letters, right? This is not the case. It's not the case that every combination has the same possibility to occur. And in fact, these actually are quite easy to break. As the book says, you know, you may have seen these in part of the puzzles or crossword magazines, things to do codebreaker things. So why is that the case? One crucial idea is that there is a frequency of letters in English. So letters appear more often than others in words. And then there's also grammatical rules that tell you that, for example, the letter Q is often followed by the letter U, right? And then there's like, there's no double W or other types of bigrams like that. And so with all this information, you can get information about the key, right? This is external information, and that contributes to greatly lower the complexity of a search, right? So to show you what this thing looks like, we're going to go through the exercise. We don't have to do all of it, but here is what the frequency table looks like. And you see the E is the most frequent letter with like 13% of occurrency, and then we have T, and then we have A, all the way down to Z, which is the least frequent letter. Here it's given in alphabetical order, but it's the same table. Okay, so let's look at this encrypted text, this ciphertext that we get, right? And what we can do is we have 298 letters. We'll make a frequency table, which looks like this, for our letters, right? So you see that we have 32 J's in my ciphertext, which is 11%. And then we have 28 L's, which is 9%. And then we have 27 D's, which is also 9%, and all the way down to these letters here. Okay, so at this point, we are using this additional information to start making guesses, right? Because if I didn't know this, I would just have the 26 factorial possibilities equally. But now I can start guessing that, for example, the most common letter, which is the J, has to map to the E, because we know that the E is the most frequent, right? So then I'll go here, and I'll map the J to the E. Okay, and I guess that this was my first key, my first part of the key. Then we look at the next letters. There were the L and the D. And according to the table, we can maybe guess that this represents the T and the A. Now, of course, this is not a one-to-one thing, right? It's not necessarily like that. So do it in this way would be a bit simplistic, but it can at least give us an indication. So rather than going one by one, it's really not likely to give us the solution. What we can do is we can take like the next few, for example, the G and the Y, right? Here I am again with the data. You see that the L, D, G, and Y are the next, say, 4 more likely, and we'll try to map them, and let's include the S as well, because they are all, say, above 22 occurrences. These next 5 letters will probably be a combination of T, A, O, and N. Here's the table there. Okay, so we'll try different combinations of these and see what makes sense. Okay, so again, I don't want to go through the exercise in full detail because you have this in the book, but you can imagine that the idea is I use this frequency table to make educated guesses, and once I have unlocked the first few, the complexity decreases by a lot. So this is another important idea in cryptography, is that the attacks are not often, and in fact almost never, like the stupid ones. Right? So what we looked at before, and I can write it here because it's an important idea, is what we call a brute force, which is self-explanatory. Brute force attack, also known, for example, as exhaustive key search. And so then it's not exactly the same idea. A brute force attack means just going through all over the possibilities. We don't do this necessarily just for the key. Sometimes what we do is, for example, try all possible ciphertexts, all possible plaintexts, and so on. But exhaustive key search is a specific thing. It means I try all the keys. Yes. Now we don't have to think about this as a real attack. It's more like the prerequisite. Yes, like if I'm designing an encryption scheme, which we haven't defined yet, but anyway, you get the idea. The first thing I gotta make sure is that an exhaustive key search is infeasible. Yes. Of course, if this is not the case, then we're not even talking about it. That being said, the exhaustive key search is like the dumb strategy, but in a lot of cases, having little hints lowers the complexity by a lot. Because if instead of 26 factorial, you have 20 factorial, this number is much, much smaller. Yes, and this again is just a hint the precise. I mean, in the books you have the entire unrolling of the exercise, and you can use other tricks, like for example, looking at the bigrams, right? So you know that th is of course extremely common in English because a lot of the words contain this part, he, an, re, and this is it's interesting of itself, especially for me because English is a foreign language, so it's interesting to understand how this works. But then you can use bigrams too. So it's not just about the single frequency, but also, as I was hinting at, there's like some sequences that never happen. So if I say, okay, this letter is probably W, but then I see like this letter next to itself, it's like, okay, this is certainly not going to be W, right? And so on. So with this, there are several ways to proceed. Basically, you use all this information together, and you can guess some mappings. So what the book does here is that it guesses that J is equal to E, like we did before, the L is equal to T, and the O is equal to H. And then you already have like a good chunk of plain text here. And you see in some cases there is like a the E here, a TTHE down here. So there's some indicative chunks already in there. So what we did L to T and D to and not D, the O to H. And then yes, you can look at some fragments, try to recognize some words. There's a lot of you can keep moving forward with the example. Once you guess some more letters, and every time you lower the complexity by a little bit, you make different considerations. And once you have enough head start, at that point, an exhaustive key search becomes feasible. You see what I mean? So it's a combination of strategies for which, like, once you get down to 10 letters left, then you can just do it by inspection. Yes. So this is an idea about security of these schemes. Now the set of letters is what we call the alphabet. So here I'm going to write it. So normally, I mean, these first examples that we are given today, we have introduced with just letters, of course. There are several other ciphers that were used up to a certain point in history. And then nowadays, of course, these are not relevant anymore in the sense that they are not used for communication, right? Everything is on computer, everything is digital. Our alphabet will switch to binary. This is what we will focus on, at least if we were doing a lot of the symmetric cryptography, right? But maybe at this point, since we still have some time, first of all, I can take some questions if you have any questions, and then I can.
Sorry, I must have missed it. What exactly is symmetric cryptography?
Yeah, that's a good question. It's important. So the idea of symmetric cryptography is the following: we have basically we have a secure place, right, with a door, right here, and this door opens with a certain key, right, and we use the same key for encrypting and decrypting.
Okay.
Which is respectively the operation of taking plaintext into ciphertext and ciphertext into plaintext.
Okay.
So in this sense, this is called symmetric. And as we will see in a few lectures, this is not, I mean, it is still a major component of cryptography, but it's not the only one. And in a lot of situations, we use an entirely different paradigm, which unlocked a series of things that we were not able to do before. Okay, so far, cryptography has been, let's say, since Julius Caesar up until the 1970s, the idea of exchanging messages securely by doing some sort of cipher. Mm-hmm. We are not going to go too deep on it, but the idea is that we're going to improve on this method of building ciphers. It's going to go from letters to binary alphabet. It's going to go from a simple substitution to substitution and other stuff. Mm-hmm. But the idea is basically this is the blueprint. Yes, we kind of scramble. It's the most intuitive way. We scramble our message to make it secure. Okay. So I don't want to talk about numbers yet because there's a stuff for next lecture. But I thought that maybe we can formalize things a little bit so that we know what we are talking about. So formally, let's say that a cipher is also known as a symmetric encryption scheme, right? Is composed of three spaces: a space K, a space M, as a space C. Sometimes it is P. Okay, it doesn't really matter. So this is the key space. This is the message or plain text space, and this is the ciphertext space. Okay, and then we have an algorithm for encryption. Let's say E, which is an encryption algorithm, and a decryption algorithm. D. Okay, so this is the formal structure of an encryption scheme. Now we know what a symmetric encryption scheme E is. So one example was the shift cipher. In the shift cipher, we have the K is equal to this is the alphabet, right? So is the set of letters A. Oh, sorry, let's do something different. Let's do 0, 1, 2, 25. Yes, because we said that in the shift cipher the key is an integer by how many positions I shift. And one thing that I didn't tell you, but you probably realize yourselves, is that this integer is limited to 25. As in, if I shift by 26 letters, I'm back to the origin, of course. And the other thing that you also probably got to yourselves is that once I go over, so if I have a V and I have to shift by 10 letters, after I get to Z, I start over again. That's why this is represented with a wheel, right? So again, we'll talk more formally about numbers next lecture, but this should remind you, this kind of cyclical structure, right, should remind you of what particular mathematical object
A cyclic group or a modular arithmetic?
modular. Yes, I'm just simply talking about modular arithmetic, right? Because like the hours in our day or several other modular ideas, right? Once I go over, I start back from the beginning. So this is kind of like modulo 26 because I have 26 letters, at least in English, and so this is really what we call Z26. Which again we will formalize in the next lecture. Yeah, we'll do a little recap. But so we can assume that for us the key space is 26 essentially. And in fact, in a sense, I mean, what is the message space and what is the ciphertext space? Yes, formally we can say, for example, that the message space is also Z26, and so is the ciphertext space, right? If we say, okay, this is just like one letter, right? And then we apply the key by doing addition. So we can identify right? For example, the A with the 0, the B with the 1, the C with the 2. This is not mandatory, it's just the most normal way. You can have another mapping if you want. We can talk later, again, more in detail about this process here, which we call encoding, which is simply the process of transforming information, right? So a code is just a way to transform a message into another form. This can be even like my voice going over the telephone line, right? Or the Morse code, as you may have heard, telegraphs, all sort of things that are transforming messages with no requirement about security, right? So the canonical encoding, if you want, for letters of the alphabet is 0 to 25 mapping, yes, with A, B, all the way up to Z. You can use a different encoding if you want, but the substance doesn't change. So net, the encoding method that you have, the encryption scheme is the same, right? And I can think of this as M equal to Z26, in which the message is just one letter. And then if I have a longer message, I just do the same thing, block by block. Or I can think of these also as M equal Z26 to a certain power, say N. And then I have like a bunch of letters together. And then my description of my encryption algorithm will be different. So normally when I think of my encryption algorithm, it takes, so the encryption algorithm is usually doing this. It's a function, right? From a message and a key into the ciphertext space. Yes? And so let's say this is E, right? And it takes, therefore, a message here and a key here and returns a ciphertext. And in this case, this is just defined as message plus key modulo 26, of course. Can you see what?
Can you move up the paper a little bit?
Yes.
Thank you.
Sorry. I can also zoom out, but then it becomes smaller. So, okay. So if I define my message space as a single letter, then my encryption algorithm is letter plus key. If I define my message space as, I don't know, 10 letters, then my encryption algorithm is different. It would be like message plus key for each letter. Right? So formally, it would be something like, if I do this, for example, is like to the power of 5, which I think is what the book was doing. If you remember the ciphertext that we had before, you see is split in blocks of 5. Normally, this is just for ease of readability. Yes, but you can define it in the same way. So then the encryption algorithm in this case would be from Z26 to the power of 5, so strings of 5 letters. It would be taking M1, M2, M3, M4, M5 into M1 plus K, M2 plus K, M3 plus K, okay, M4 plus K, M5 plus K, right? So it's the same thing in this sense. The block size, in other words, we can, all of this is mod 26, yes? So with a shift cipher, we have, in a sense, a freedom to define our plaintext space and ciphertext space. But one notion that you can already extrapolate is that we talk about blocks of information. Yes, and so normally these things are called block ciphers. Because they apply the key to a block, and then once you exceed the block length, you just like do it again. So however long your plaintext is, you're gonna have to split it somehow. Okay. So in this case, it doesn't matter if I define my plaintext space as a single letter or as 5 letters or 10 letters. In any way, this is still well defined. Okay. And then the decryption, just so you can see that this is actually a symmetric scheme, would really be C plus K, mod 26, minus K. Okay. So it's really using the key in the opposite direction. S really is like turning the key right or left in the door. So a shift cipher really incarnates the essence of a symmetric encryption scheme. Now with the substitution cipher, right, you can try to see what these objects are. Obviously, your key space is not just one number, but it would be a mapping, right? So if you want, you can represent this as a string of letters, right? So then it would be a string of 26 letters. Yes, then you can say my key space is Z26 to the 26. But they would not be accurate because that would allow for like repetition of letters. So you can formalize it. You can say, for example, it's a function from Z26 to Z26, and then say my key space is the set of functions from Z26 to the set of bijections. And then you can formalize, okay, then my message has a certain block length, my ciphertext has a certain block length. Another characteristic that you will see of symmetric cryptography is that usually the ciphertext has the same length as the plaintext. There is no expansion. This is a typical quality of symmetric cryptography. And so what is really the crucial point? We have these 5. So this is the definition of a cipher. We have 3 spaces: the key space, the plaintext space, and the ciphertext space. And we have an encryption algorithm that takes a message and a key into a ciphertext. We have a decryption algorithm that takes a ciphertext and a key into a message. For plaintext, I prefer plaintext because it's more accurate, but sometimes you see message. Right? So this takes a ciphertext and a key into a plaintext. And of course, the important requirement is that the encryption is undone by the decryption. So we have the decryption of the encryption of a message with a key returns the message. Okay, this is correctness requirement. Yes, so normally you call correctness, and this will be for all keys and messages. Okay. Sometimes instead of writing E of M and K as an argument, you can write E of M with the key K and D of C with the key K, right? Rather than using a pair, because the key is always used, you put it as a subscript. So what you can observe, again, the principle of symmetric cryptography is that the EMD functions are inverse from a logical point of view. Okay, and for this reason, we said before that my function is to be one-to-one, otherwise my inverse is not guaranteed to exist. Okay, so we defined the crucial building blocks: key space, plaintext space, ciphertext space, encryption and decryption algorithm. Great. There's a couple more things that I wanted to say. Having said how we can build a scheme, is it a good scheme or a bad scheme? There are some requirements, right? First of all, we have to have that given key and a message. It is, let's say, easy to compute a ciphertext. Okay, this is a trivial requirement. Of course, the encryption operation needs to be practical. Okay, same thing. Given a key and a ciphertext, it must be easy to compute the decryption algorithm. Okay. And then we have some requirements about security. And then we can define this more in detail later. But traditionally, you want an attack to be hard. So it should be infeasible given a ciphertext to recover a plaintext without the key. So very roughly, and we can formalize that later. Given C hard compute M. Okay, so given just a ciphertext without the key, you shouldn't be able to recover the plaintext. This is normally what we call one-way security. It should also, of course, be hard to recover the key itself. And all sorts of security requirements that, again, we will formalize later. Okay, we will give more examples of ciphers, and right now I just want to conclude it with one emphasis. Of course, both parties use the same key, right? And yet the key should be hard to achieve, because as soon as you get the key, because of these two requirements, computing the plaintext should be easy, right? So one crucial point, like in a real door, like a real crypt, is that the key has to stay secret. Okay, so everything else seems very reasonable. So far, we've seen two trivial examples. We will see more advanced examples, but they always verify this condition, right? So encrypting and decrypting is always easy, given the key. Most of the times, it's a matter of doing shifts, substitutions, or other things that I can spoiler for you, like permutations, right? There are other ways of doing ciphers which involve like moving the letters around, or combining these things together, but in the end it's still an easy process. It's only hard if you don't know the key. And as we saw before, even if you know some partial information about the key, this already becomes dangerous. So the crucial point of symmetric cryptography is that it has some very good features, and it was used for centuries, but it's very delicate. And the more security you want to achieve, the more complicated methods you're going to have. And then you have these very complicated keys, because again, we will see more examples, but you can imagine that to achieve more security, you have more complicated methods, and then, for example, longer keys, right? And then there was a time, about the beginning of last century, in which like there were people going around with these giant rolls of paper that would contain, no, I'm not kidding, you can look it up, there would be like giant rolls of paper keys. They would be securely transported from one location to the other, right, to encrypt sensitive information. Of course, this is not practical, right? So one cryptography bad feature of symmetric cryptography, which prompted the idea of what we will see for a large part of the course, which is the asymmetric cryptography, is that you have to exchange the key securely, and this cannot be compromised. Okay, and this is evident from what we defined in terms of ciphers, because if we compromise even just part of the key, then the security of the entire encryption scheme is compromised. Okay, as I said, we have more complex security requirements, which we will define more in advance later. Of course, the one-way requirement, if you want, is the most natural one, right? Seeing a ciphertext, an encrypted message, you shouldn't be able to read it, to decrypt it, but we can formalize different attack models, and capabilities of the attacker, how much does the attacker know, right? For example, I may want to say, oh, my cipher is secure even though the attacker knows, I don't know, half of the key, or is able to see like some parts of decrypted plain text, right? So you may want to ask for stronger security guarantees, and depending on what cipher you're using, sometimes they entirely crumble, sometimes they stay secure. All of this can be formalized, and it's very interesting, the discussion about security models and attacks and roles, and we will have it later. But today I just kind of wanted to give an introduction to the ciphers. So then the roadmap will be, we will start doing a little bit of a recap, because I just want everyone to be on the same level with the modular arithmetic, which you already see is going to be major. And then, of course, the more algebra you have, the better, but we will fill in when necessary. I mean, the purpose of the course is to go through the math, right? And then a little bit down the road, we will start talking about the real math, which is the one not behind the ciphers, but behind the actual asymmetric schemes that we use today. Okay? So far, we've just seen, okay, I just wanted to leave with the idea that basically the simple cryptography that has been used for ages corresponds with the idea of taking a message and securing it by scrambling it in some simple way, which doesn't alter its length. It's just like mapping things to each other, right, and using the same key to encrypt and decrypt. And then we will see, we'll have a couple of lectures to recap the math. Then we will see how we can change this and why we need so much math to do things in a more efficient way. Okay. So that's it for today. Now, if you have questions about the course itself, we can go over them together, and then we're done for today. I don't know, it's supposed to be 12:20, the end, but it's the first lecture, so.
There is no computer code or anything in this class, right? It's just like the ideas that we learned.
Yeah. So there's a bunch of reasons. First of all, it's a math class, so so the actual algorithms are not the focus. Of course, if you know how to program or use computational systems, it helps, but it's not a requirement. It cannot be a requirement. And and second of all, if we did have to make it a requirement, it would involve like more time in the class. But if you are interested in any of these things, both, for example, I don't know if you know some programming language, or there are also some softwares. One is open source and it's called Sage, that you may have heard, Sage Math. One is based on Python, and one that is not open source, but we do have a license which is called Magma, and it's based on C. And they both essentially are super beefed up systems for like algebra things, so you can build your fields and your rings and do operations in them, and build matrices and invert matrices and blah, blah, blah. They're very, 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 very intuitive, because it's like if you have to compute the determinant of entries, the command is determinant of the or whatever. It is really as you read it, but of course takes a while. Again, it's not going to be a requirement, but if you're interested, I can send you the website, the documentation, something like that. For typing, normally mathematics we use LaTeX, which you may have seen. Again, it's very high-level language, but it's just not a text editor. You just write your file, and then it gets compiled, and then you have like all the symbols and things, and then you're able to like write things like this. Exactly, right? This is all written in LaTeX with the subscripts and the superscripts and equations and things. So again, this is something that is appreciated, but not necessary. Okay. Normally we use that to write everything that involves math rather than handwriting, or using like weird editors with like formulas in it. Again, if you're interested in that, I can give you some pointers. It's very easy. LaTeX is free to install, and it's addictive. Like once you start using it, like I just use it for my CV and for for everything else, just because you get precise control of where things happen in the document and imagination and things besides the math formula. Okay, so as far as technology is concerned, none of it is required in the course, because we're going to like really focus on the math. Of course, if we do need to do like some complicated calculations, maybe I'll bring, say, Magma to the classroom or something. I can access it from my account. But I just kind of want you to get the principle of things rather than doing the actual I mean, I don't want to, like it's counterintuitive. Like I don't want you to do like the actual math. I want you to understand the structure, right? And plus, the stuff at some point we will start computing things that we don't really make practical examples of, right? So it's going to be more abstract side. Do you have any other questions on? So one thing, of course, this is a 4,000 level course, so it's not going to be the same as like my calculus class or anything like that. I'm not planning on having graded assignments or anything like that, and I'm not planning on giving like specific homework. Normally, I just invite you to have the book, and if you do it little by little, it's going to be very easy. Because at the end of each section, there is like, section 1.1, which is what we covered today, about basic ciphers. Right? And there's some really simple exercises which you can go over at your discretion, because again, I assume, we're in like a 4,000 level class, so you have the maturity to say like, I didn't really understand how the substitution cipher works, right? Let me make an exercise on this or whatnot. And then maybe if it's really clear to you, it'll be a really easy exercise to do. This book is kind of it's an interesting book because it's kind of like a hybrid between a text, like it's not a calculus textbook, but it's also it's not like an academic, it's kind of like in between. So the exercises, some of them are like really like to practice the notion, but some of them actually give you some nice insight into the topic. So even if you're like, I completely understand this section, it may be still like worth skimming over the exercise because like some of them will teach you new things and will show you some new concepts and give you like, now I understand why this is like that, right? So as a rule of thumb, basically, I can tell you what we covered. Today we roughly covered section 1.1. We did not go through the entire, because then it's kind of boring, but like, decrypting the big substitution cipher thing. But basically we covered 1.1, so you can just feel free to go over the exercises at the end of 1.1. And you'll see, I can show you here. You see like, 1.1, simple substitution cipher. Build a cipher wheel, which you can do really quickly, and then encrypt a message using that, just to try. And there's a bunch of exercises of this nature. Yes, just to play around. And then next lecture we'll do 1.2, 1.3, and whatnot. And I will tell you each time which sections we're covering, which exercises you can go over. So it's just practice. I'm not planning on assigning any number of these or grading any number of these. And as far as evaluations, I think my idea is we will just have one midterm and then one final exam. And it will be normally a collection of things similar to what we saw. Again, we're not going to use any computational system or anything like that, so it will not be necessarily like hands-on things, but some questions may be more like a essay, like, okay, describe what a substitution cipher is, what is this key space, and blah, 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 in detail, okay? So it's going to be more on a notion point of view rather than actually, because again, you will realize very quickly that after when you do cryptography, there's no point in doing like the little toy things, and there's very little you can actually play around with rather than describing how the attack works and all. Okay, so that's my idea. So we don't have to worry about the midterm for a long time. It's the first class, but the idea is that just go over the notions and recap like, okay, what's a substitution cipher? Yes, it works like this. The space is this, blah, blah, blah. And then the various other things that we go over. Okay.
Is the midterm and final going to be online or in class?
That's a good question. I haven't really thought about it yet. But some people are not here, so we can't. But maybe, for people that do come here regularly, I can have them in person, and then I can arrange for the other people to have them online, or maybe I'll just do a take-home exam or something. I haven't really thought about it yet. But because it's going to be more essay style type for the most part, I think it's probably okay to do it remotely anyway. So once I figure out what the exam is, I'll figure out the mode. Normally, yeah, it can be done online for sure. Okay. But if you plan to attend, it's great because first of all, I don't have to talk to an empty classroom, and then I think it's much more. Yeah, I thought about doing the lecture live on Zoom like I did last semester. I just didn't really enjoy it. being able to interact even like this, even with the distance, the mask, and everything. If you guys can ask questions, it's much easier. People that are home will get the recorded lecture, but of course, then they don't get to ask questions or things. Of course, you can come to office hours, you can email me, you can have virtual office hours, all sort of things. But the core of the class should be in the classroom, yeah. And I'll figure out a way. Hopefully, this works with the recording. Figure out a way to have the recordings up one way or another. If you want to look at this. And to conclude, so if you have the book with you, it's great because you can integrate what I say in class. The things should be decoupled because I don't have the time to go through all the sections. And as you see, already there's a huge plain text with all the long key and stuff. I just kind of want to give you the flavor during the lecture, and then you can finish reading the chapter and integrate the things. So there's the one thing that I recommend is just having the book. I don't think it's even very expensive. Because it's not one of those big calculus textbooks, whatever. So I think it's I don't know, $20. I'm not sure, something like that. Okay, you can find it on Amazon or whatever. Cool. So I'll see you Friday. And I'll probably send out an announcement on Canvas as to where the recordings are going to be once I figured out the actual tech. Today, we'll see what happens. Cool. So let me stop this recording.